Let me begin with a word of prayer. So we'll just review until we can get Shane here. So, Heavenly Father, we thank you for this day again. I thank you for this class and this time we have to study your creation. Help us to glorify you in what we do this day, Lord. In your name I pray, Lord Jesus. Amen. So last time we defined oriented simplicial complexes. Yeah, complex. And so we're I will get quickly to the point. So we defined basically polytopes and the so-called chains. So like so we had K, A. Oh yeah, isn't that a great quote? This book is one of the joys of this book. Oriented simplicial complex. Then CMK, it's the set of formal linear combinations of M chains from K. So what I mean by that is sigma bar looks something like a sum I. Now I doesn't have to be M, but we have A sub I. I mean, I equals, well, I don't know how many there are. It's K, let's say K. Oh, wait a minute. This is supposed to be M, right? I think this was M. This was M. A sub I, sigma bar I. And so like each sigma bar I is an oriented, do I have this right? Hold on a second. I think I've forgotten my counting. 2 simplex, M simplices. Yeah, my bad. That's not M. This could be K, whatever. Is an oriented M simplex. So just to be, what do those look like? So a 2 simplex is something like P0, let's do 1 simplex first. 1 simplex is 0, P1, P0, P1. So it's a line segment, an oriented line segment. A 2 simplex is like a triangle. All right, so I'll draw the picture here. Three simplex so I'm just labeling them. I'm labeling the simplex by its vertex. It's the convex hull of its vertices. So it's like, basically the smallest convex set which contains these points. That intersection of all convex sets, which contains these 4 points, defines the convex hull, which is just a fancy way of saying it contains all line segments that connect the points involved, and all line segments between, yeah, like shrink rapid, exactly. Perfect. That's very good. I like that. So at the danger of, there's an edge back there. Okay. I will not attempt to draw the 4 simplex, okay? But obviously, nothing's stopping us from doing that. This is completely algebraic. And so what a simplicial complex is a collection of simplices that satisfy 2 axioms. And those axioms are, 1, if you have a subset, so like if we have this, set of points S is an element of the simplex, and T is a subset of S, then the simplex generated by T, the convex hull of T, is also an element of the simplicial complex. So that's just a fancy way of saying that if the triangle, for example, is in the simplex, then all of its edges and all of its vertices must also be in it. And then the other thing is that if two simplices meet, they have to like intersect along a common edge. So like the intersection of two simplices must also again be a yeah, something like that. What that looks like here is essentially S1 intersected with the simplex generated by S2 has to be the simplex. It doesn't have to be it. No, it does. It has to equal, rather, the intersection like this. So if his simple sentence to encapsulate the idea is if 2 simplices meet, they must do so along a mutual face, right? So, all right. So, all right. That was the basic setup. We spent about an hour on that, and then we introduced orientations, which is just to say this comes first, that comes second, and I can sort of illustrate the orientations with arrows on my diagrams, right? Like here to here, this one goes 0 to 1, 1 to 2, 2 to 0. It's a little bit trickier there, but, well, let me show you how I think about illustrating the orientation on a 3 simplex. I do it in terms of the orientations. So for the 1 simplex, I do it in terms of the orientation of the line segment. For the 2 simplex, again, I do it in terms of the orientation of the edge of it. And also, this is a solid. Understand that this is a solid tetrahedral kind of thing. Well, the other thing to introduce is the boundary operator. You see, the boundary of this is defined to be P1 minus P0. All right, and that's the kind of formal linear combination I'm talking about. We don't actually write down the coordinates for the points in Rn and subtract them. It's not that kind of subtraction. It's a formal subtraction. We're actually using the points that form the simplicial complex as basis elements, for example, in the space of 0 simplices. The 0 simplex is just a set of points, or a point, rather. So here, like C1k would be like formal linear combinations of 1 simplexes. So the basis elements in that space are actually line segments, theoretically. We'll see this in the calculations we do in a second, but the boundary operator here, let me put a sub 1 on this, a sub 2, is, well, here's the way it works. You delete the first one, and you leave the last 2. And then, as you go over, you put minus and plus. So then minus, you delete the middle one and leave the first and the last unpermuted, okay? And then I go plus, minus, plus the P0, P1. Notice how this works. See how that goes? 1, 2, 0. Oh, notice the minus on the 0, 2, right? So if the rule for orientation is that if this is, if we absorb the minus into the oriented simplex, that reverses the orientation, but the rules for this is just we switch the order. to disorient a line segment, you just switch the beginning and the ending for the ending and the beginning. So like that movie, you know. But so here, see, now we go 1 to 2, 2 to 0, 0 to 1. The boundary operator algebraically builds in the natural orientation of the boundary of the simplex. And it works down here too. So like the boundary of sigma 3 is, let's see here, P1, P2, P3 minus P0, 2, 3 plus 1, rather 0, 1, 3 minus 0, 1, 2. And if we absorb the minuses and do some flippy-flopping, we've got 1, 2, 3 plus 2, 0, 3 plus 0, 1, 3. Don't worry, we haven't done anything new yet. 0, 1, 1, 0, 2. And check out how this works. So like 1, 2, 3. If you look over my picture, we go 1, 1, 2, 3, right? So I like to just draw like a little swirly on that face. It's like that. And how about 0, 1, 3? Over here, right? So there's also like that, you know? And if you look at it, so it's the right-hand rule. We're inducing the outward orienting normal for this one. And on the back, you'd also find, and on the bottom, you'd also find outward orienting normals. So like algebra of the boundary operator is inducing the correct orientation of the faces of the tetrahedron simply from this very simple algebra. So this is, and then the last thing we did last class was first of all, we gave a general definition for the boundary operator, and we proved that if you look at the boundary operator as a mapping from, where's it go? It takes in M chains over K, right? And what's it output? I mean, to be fussy, we should probably call this partial M because there's different ones. I mean, it's not technically the same map every time, right? Like this is really the 1 boundary, this is the 2 boundary map, this is the 3 boundary map, truth be told.
So it's going into CM minus 1.
That's right. And we had the big theorem we ended last class with was that the boundary squared is 0. The boundary of the boundary is no more. And so that's where we are. But now Shane is left, so I'm unable to start. So that brings us to section 5.2 of Rentland, which is on homology. All right. And again, just to make clear where I'm working from this delightful little book called Manifolds, Tensors, and Forms, an Introduction for Mathematicians and Physicists by Paul Rentland. And I find this to be, it's a wonderful little book. All right, so oh, thanks. I'll take it. Have a good evening. Oh, make sure I talk to you tomorrow about the extra stuff to do, okay? Yep. Bad. Oh. All right, so Definition. A triangulation of a topological space X, right, is a simplicial complex K, which is homeomorphic to X. All right. So, for example, if we look at the the tetrahedron, right? This thing we're just looking at, right? So if we, I'm trying to think what's the right notation. I have to be careful. So I mean, to be fussy, the simplicial complex is, it's not just the totality of the points that form the tetrahedron, right? It's the set of all sub-objects of it as well. You know? It's a set of sets. But if you'll allow me the abuse of just referring to the largest set, the union of all those, this is, this tetrahedron is homeomorphic to what? What do we call that? The sphere. The sphere, right? Yeah. But we can let me be a little bit more vague, because it's not just the tetrahedron. We can do this thing, right? The n-dimensional tetrahedron. I don't know what's he call that thing. Oh, he doesn't. He's smarter than I am. He just refers to it by its formula. That's smarter. Sigma bar. This thing is sort of, the triangle. This gives you the triangulation. I can't say words today. Triangulation of the n+1 ball. Not sure that the counting is right there. Does that seem right? Like I think this is the, if we're talking about 3 dimensions, right? If I'm talking three-dimensional, what is this? This is the 3 ball, I believe. Because the labeling of things is dimension. This is a B3. It's a 3-dimensional manifold. Oh, yes. I'll take it. Oh, well, thank you. You can tell Mary nothing, of course. Tell her it was easy. Tell her it was the most fun you've had this semester. It wasn't? Oh, man. Well.
Is the first one supposed to be 0?
Wait, this is recording. Wait. See ya. 4164, is that what you said?
I guess my location is known. Okay, so all right, so if this is I think this is the 3 ball, isn't it? In 3 dimensions, B3. So. Like the boundary of the. He says the boundary of Bn+1 is Sn, and I think I agree with that, because the boundary of the 3 ball is the 2 sphere, right? B2 is the disk. The boundary of the disk is the circle. So, So I think there may just be a typo there. Because he says that this is a triangulation. Good grief, I can't say that word today. Triangulation of the n+1 ball. I don't buy it. There's like the tetrahedron is homeomorphic to like the regular 4 vertex. Just the tetrahedron, this thing, solid tetrahedron is filled. It's a 3-dimensional shape. It's got 4 corners, and I'm pretty sure it's homeomorphic to the 3 ball. So I think it's not n. So this has n+1 points, right? For 3. I think it's n ball, right? N ball. Like example 2, if I just talk about a triangle, right? This is homeomorphic to the what? The 2-disk, yes. So, I mean, don't ask me for the formula, but I think it's clear, What would the, would you like to know the kind of proof I was given in my graduate topology class about the homeomorphism? I think it was a square and why is the square homeomorphic to the circle? And his proof, or maybe the cube, it was the cube and the sphere.
To actually find the homomorphism?
Oh yeah, how did he find it? I mean, he just drew a picture, is what he did. It's just like, it's clear. Basically you've got this, you got that, right? And you just kind of like, just kind of, well, that wasn't even what he did. He didn't draw that. He had a better picture. He just basically did something like, you just essentially just take these points and map them like that. And that's continuous, and that's the homeomorphism, and it's clearly, it's clearly bijective and continuous, and as such, the square is homeomorphic to the circle. Yeah.
Could you, I'm just thinking about the boundary, but I guess you could map the boundary to whatever, like, normal vector through the...
Well, yeah, I think if you wanted to do it if you like sort of from the square to the disk, just take this idea, rinse and repeat, right? Just do it on like ever smaller squares to ever smaller circles, finally mapping the dead center of the square to the dead center of the disk. It's clearly continuous, right? But I don't know. I guess you make the proof like a homework problem for grad students. That's what they're for, right? Working out these kinds of problems that would never be publishable anywhere, but could very well eat a week of your life, But it's good experience, so you have that to look forward to. So, anyway, I'm not going to prove these things are homeomorphic. I'm just saying that intuitively speaking, it's somewhat clear that the tetrahedron is homeomorphic to the 3-ball. That a shaded-in triangle is homeomorphic to the closed unit disk. And if I was just to look at the edge, just the triangle itself, not the shaded-in triangle, it's fairly clear that that's homeomorphic to the circle, right? So what I'm telling you is that we have triangulations of n balls and of n spheres, right? Those spaces are triangulable. What's interesting is that there are spaces which are not triangulable. There are even topological manifolds which are not triangulable. So this method of understanding the topology by finding a triangulation of it and calculating some linear algebraic data, as we will soon, is not totally general. He mentions in here that there's something called the E8 space, which is a physically interesting space that has to do with like E8 cross E8 heterotic string theory. It's an exceptional, it's one of those exceptional objects. There was a really cool picture that came out about it about like four years ago or so. Some guy had a theory of everything that was based on one of these. Every so often somebody comes up with some new theory of everything and people get excited about it, and then inevitably it only goes so far. Okay, so anyway. So all of that, you know, exotic things aside, you can usually find a triangulation of manifolds that we're interested in, all right? And so if we can find a triangulation, we can define homology, all right? So let's get to that. What do I mean by homology? So once we have a triangulation, that means we have a simplicial complex that's related to the space in consideration, right? And so an M-chain definition, an M-chain C-bar for which the boundary of C-bar is equal to 0 is called an M cycle. All right, an M cycle. And the space of all M cycles is labeled, we say C-bar is an element of Z M K, all right? That's the space of all M cycles. All right. The Z is German for Cycle. So these things were done back before Germany deleted itself from a lot of, I mean, Germany was the center for mathematical progress before World War II, remember? And then something bad happened and we got all their scientists, so. But we still remember the letter Z in the math. We still have the integers, right? It's not I, it's Z for, right? It's this German. Eigenvectors, also an artifact of the German prominence in mathematics, so forth. Let's see here. Anyway, on the other hand, if an M chain, next definition, and M chain C bar such that C bar is equal to the boundary of C bar prime. That's not a derivative, it's another, you know, maybe I should even just use a different letter. I guess I'll stick with it, that's what the book has, but what would that make C prime? C bar prime would be an element of what? What would be a what? An M, no, not M cycle, but an M plus one chain, right? See, because I'm taking the boundary of this thing and getting an M chain, it must be that it was an M plus one chain, because the boundary reduces. It taketh away. All right, so two M cycles whose difference is an M boundary. Oh, an M chain, I neglected to tell you what this is. Is called a what? Duh. If I could finish my definition before I go on to the next one. An M boundary. So you've got boundaries and you've got cycles. And so then what? Can you guys tell me, what can you tell me about a boundary? What about is a boundary a cycle? Is a cycle a boundary? What do you think?
boundary is a cycle.
Aha, so observation. Partial C bar equal to partial C bar prime equals to 0. So if C bar equals to partial C bar prime, then C bar is an element of ZMK, right? In other words, you've just shown that BMK is a what? It's a subset of ZMK, right? Every boundary is a cycle.
You didn't define B and K.
Oh, my bad. Thank you. I guess I should do that, huh? But it doesn't have to be the other way. I mean, not every, these are not equal, okay?
Yeah.
There's no reason for the other to be equal. So here's a definition. Two M cycles whose difference is an M boundary are said to be, let's see if I can say this word today, homologous. Homologous. And so the notation for that would be something like Z bar 1 is equivalent to C bar 2, all right? When Z bar 1 minus Z bar 2 is an element of the boundary of some C bar, right? I mean, more to the point, it's when the difference is an element of what? I mean, fine, I guess we can say that. Boundary of C bar. Another way to say this, of course, would be that Z bar 1 minus Z bar 2 is an element of what? The B, right? BMK. All right? And here's what he says. He says, the set of all such equivalence classes is the mth simplicial homology group, denoted HMK. Let's be a little bit more precise. It's a quotient vector space, in fact. HM is equal to the ZMK quotient BMK. Right? In other words, it's the set of equivalence classes of M cycles. So you got like, you know, Z, like that. I guess what's our space of we start calling them cycles, but I think they're what's the difference between is a cycle a chain? I lose track of words at some point in here. CMK is a set of formal linear M chains. I think chain and cycle are An M chain is called an M cycle. Oh, I'm sorry. Cycle means that the boundary is 0. I got to be careful. Chain does not. I just like to say cycle. The problem. So Z is a M chain. Okay, yeah. So Z and L is CMK, right? You could write it like this, you know, it's equal to, I think we could reasonably say Z plus BMK, if I'm not wrong here. Now, this is not in Retland, and it's probably not even helpful, but my point is this just a quotient vector space where we're so I'm assuming something, aren't I? I'm assuming that, you know, that ZMK is a vector space, right? And also that BMK is a subspace of that vector space. And so is that even clear from what we're doing? I think it's relatively clear because ZMK is, what is ZMK technically? Let's write it out. ZMK is what? It is Z in CMK such that what? The boundary, the mth boundary map acting on Z equals to 0. Can you recognize what this is? What is this in terms of like Math 321? Kernel, yes. Is the kernel, and is this a linear map? Well, yes, the boundary map is a linear map by construction. We defined it on the basis of formal M-chains, right? We extended linearly, whatever that means. I mean, it means that we made a linear transformation out of it, an honest one. So this is a linear transformation. And so this is a subspace of the vector space CMK. And our observation is essentially the subspace test. That's the start of the subspace test, right? It's a subset. We've already got that the boundaries are a subset. What does it take to show that the boundary is actually, why is it that BMK is a subspace of ZMK? You guys tell me? I mean, to check it, I should do what? I should maybe do the subspace test, right? Shall we do that? Pick two boundaries. Let's say, what's my notation? C bar and B bar in there. Then C bar is boundary of C bar prime, and B bar is boundary of B bar prime. So if we look at C1, this being a real constant, let me use alpha for a constant, alpha 1. Why am I putting a 1 on it? Just alpha, a real constant, times C bar plus B bar. Well, that's alpha times the boundary of C bar prime plus alpha times the boundary of B bar prime. And since the boundary is linear, I can rewrite this as the boundary of alpha C prime plus B bar prime. Oh, woohoo! Therefore, alpha C bar plus B bar is an element of, well, BMK. But I've done it for an arbitrary real constant and an arbitrary pair of boundaries. Therefore, we've passed the, almost there. What are we missing? It's a subset by our observation. It's closed under, take the constant to be 1, we've got additivity. Take the boundary B bar to be 0, we've got homogeneity. There needs to be at least one, and we need to prove it's not empty. So what would you do? Zero, right? Just use the zero cycles in there, because the 0 is the boundary of the 0. So there you go. It's a genuine subspace. And if we have a vector space, we can form the quotient space by a subspace like this. And what's the deal with that? Like, what's the dimension in this context? Do you guys know how that works? What's the dimension? So this quotient space is called the mth homology group. So what is the dimension of the mth homology group? Do you guys know the linear algebra here? What is the dimension of a quotient space? Do you guys know?
Is it some factor of the dimension of?
So have you guys never looked at quotient vector spaces before?
No.
Oh man, dang it. All right, short detour.
If it's a group, I'd imagine the cardinality of zero is cardinality.
Well, I mean, there are parallels between group theory and vector space, but cardinality is dangerous because the cardinality of any finite dimensional vector space over a field of characteristic 0 is the cardinality of the field. So cardinality isn't particularly insightful with regard to vector space dimension, unfortunately.
We look at the basis vectors, right?
Basis vectors is where it's at. So I'll be just give you guys a quick example or two here. What example am I on? 3, 4? I don't know. I'll say 4. If we take V equals to R3 and W equals to, say, the span of E1 and E2, we could look at E5. We could again look at V equals to R3 and W just being the span of, say, E3. Then in this case, the quotient space of V by W has the form ABC plus W. That's like a typical element, right? Forgive me if I just be a little bit vague. But because this is what that looks like, the rules are that I can absorb multiples of the last two things into W. If the difference of this and another, well, anyway, so two cosets are equal if their difference is in W. And so this, by the rules of the mathematics here, is that. Right? So it turns out that the basis for V by W is actually just this. This one, if we look at the quotient space of V by W, you got things of the form, again, A, B, C plus W. All right. But by the rules here, I can absorb the C and I get something like A, B, 0 plus W is my typical element. And so I can rewrite this as something like the span of E1 plus W and E2 plus W. So like in here, the quotient space, what it's doing is it's squashing everything in the subspace to a point. So if we're squashing by two-dimensional subspaces R3, we're just essentially identifying whole planes as points. So it's like replacing R3 with a line. This one, we're taking whole lines and squashing them to a point. So we're replacing all three with a plane. Yeah. So you
Did you for example, or did you mean to do like E2, E3, or something? Example 4. Because for example, if you did E3 and then you dealt with the third column, but example 4 you did the E1 and E2 and then you dealt with the second and third.
Oh, I'll fix it. Gotcha. Thank you. So, care to tell me what the dimension is? Well, in both of these examples, yes, but wait a minute, no. Sometime.
Example would be 1, B2.
I mean, yes, the dimension here is 1, the dimension here is 2, but what's the dimension of V mod W? There you go. And you can prove this in general. Like, all you do is you take a basis for your subspace, you extend to a basis for the whole space, and then you prove that everything that's everything, and then you simply look at the representative, like the cosets taking the basis as representatives, and you can show that you can get rid of all the representatives from W and just keep the ones that are outside, and that gives you a basis for the quotient vector space, the number of which is dimension of E minus W. It's not a hard proof. It's just sometimes missed in 321. So, but that's it. That's it. So once you know that, when I come back and ask the question I asked before, it becomes an easy question, because it is an easy question. What's the dimension of the mth homology group? It's what? It's the dimension of the m cycles minus the dimension of the m boundaries. And this is kind of important because this also right here is called the mth Betti number. And it has a notation. It's called beta sub m in here. He says beta sub mk basically counts the number of m-dimensional holes of K. Counts the number of m-dimensional holes of K. All right. He then has a whole page where he discusses a more topologically sophisticated version of what we're doing, and he elevates the discussion from this simple, very concrete triangulation, right, where we're looking at an oriented simplex, to he starts talking about singular M chains, all right, and he talks about, you can talk about singular cycles and singular boundaries. These are sort of continuous images. You can imagine kind of like a continuous image of the triangulation forming this set of singular M chains and so forth. And it's a somewhat deep theorem. Well, I don't know how, I shouldn't say it's that deep, I really don't know. But it is a theorem of topology nonetheless, that the homology that you calculate from the singular M chains and the homology you calculate from these concrete, from the simplicial complex, it's the same. So if we find a triangulation of the space, we can calculate the homology from the triangulation, and we'll automatically have understanding of what the homology would be if we were to study the singular M chains, which is nice because singular M chains are kind of scary, whereas this stuff is pretty concrete. Like, let's do a calculation. So the calculation we have here is to look, we'll start with the circle, I think, is where we start with. So this is his example 5.4. All right. So we'll start with the circle. What is it? What did I do?
This is fine. We'll start with a circle while you're drawing a triangle.
Oh, yeah. But, you know, okay, great. That's actually his picture for the singular. There's a picture of the singular cycle, so to speak. Oh, anyway. So he says we want to compute the homology of the circle. We need to compute the Betti numbers of K. All right. So just it's helpful to draw a picture, I think. Let me start with the, goodness, I'm trying to think. So I can talk about Z0, right? Z0 of K, right? And then that would go to Z1 of K, Z2 of K, and so forth, right? So this would be like the 0th boundary, the first boundary, Oh, there's something I'm sorry, I'm not, my bad. It's not what I should write. There's something I got one part of this already, but there's something else I should say before we get further. What is, so we cycle is the kernel of the nth boundary. What is, so I mean, to recap, the kernel of the nth boundary is the ZM cycles, right? What is the image of the M cycles, let's say? What's the image under the boundary map? What's that? That's B what?
M-1, right?
Right. Yeah. So that was the thing I should have mentioned, is like the image of the boundary map also has to do with the boundaries. All right. And so getting to the point here, what's a formula for beta M? How would we calculate that? It's the dimension of what? Of ZMK, right? Minus the dimension of what? BMK? But what is that in terms of the mapping here? It's the dimension of the kernel of the mth boundary map, right? Minus the dimension of the image of what? M plus 1 boundary map. All right. So we really just need to calculate the dimension of the kernel and the image of the different boundary maps. And once we know that, we can piece together the Betti numbers. Right? So that's essentially what's done now. So let's see here. We'll start with, let's see here. So we'll label, this is, 0, 1, 2, right? So there's just one, so we're not talking about the filled in, just a second here. All right, so every zero chain is of the form what? Let's just get this straight here. So zero chains, they are things of the form like C0, P0, plus C1, P1, plus C2, P2. All right, that, such that C0, C1, C2 are in the reals, that is C0 of K here, right? It's starting to get really, really old writing of K. Since there's only one K in the example, we could probably stop writing the of K if you guys want. I don't think there's really much danger for confusion. Okay? So, sorry about that. Yeah, sorry about that. How about one chains? You've just got, this and this and that, right? So you've got things of the form, let's say, I'll use a different letter. I guess I'll use a different letter. B0 times, I don't know, P0 comma P1 plus B1, P1 times P2. And I may be messing up the calculation in the book right now because I'm ignoring it, such that what? Such that B0, B1, B2 are real, right? So that is your C1. Okay, fine. No, I'm not writing it. I'm free. So, how about two chains? So our simplicial complex is the triangle not filled in. There is no two chain. So C2 here, it's big fat 0. So both in this example, both 0 chains and 1 chains are three-dimensional. They're both three-dimensional vector spaces. All right, and if we look at, so let's see here. Let's work on the first one. So we already know that the 0 boundary operator acts on C0 to give us what? Big fat 0, right? The boundary of points is nothing. Nothing. Right? So by assumption. So this tells me that the kernel of the 0 boundary map is all of C0, right? So we got that. What's the image of? Okay, so that's it for partial 0. How about partial 1? If we look at partial 1 acting on a typical 1 chain, what happens? Can I save myself some writing if you guys don't mind? Let me assume that my element has the same labeling. Let me just call this thing like sigma bar. So sigma partial 1 acting on sigma bar equals to what? We got what? We got B0 times what? P1 minus P naught, right? Plus what? B1, P2 minus P1. Plus B2, P0 minus P2. Are you guys with me? So, I guess I have to erase this stuff over here, sadly. So how do you calculate dimensions of kernel and image? What should you do? When you're trying to calculate something in linear algebra, there's kind of, I guess it depends. Sometimes there's some slick way to do it without choosing a basis, but here, we should just choose a basis and make the calculation plain, right? So what's my basis for the zero chains? What's my basis for the 1 chains? So I would say C0 is the span of P0, P1, P2. All right, I'm going to call that. I'm about to use beta, but that's unfortunate, isn't it? So there's my basis for the 0 chains is that. Let's say C1, on the other hand, is the real span of what? Let's use the same ones I've got up there. So P0, P1. What's my next one?
P2 minus P2, P1.
P2, P1? Okay.